It's certainly my pleasure to participate in this series. I think it's a really great idea, and I love the setting, so happy to be here. So this evening I'd like to again talk about this issue of air pollution and how it's now turned into a global phenomenon, and it has important implications for both how we manage air quality, but also its link to climate. And so tonight I'm going to I'll give you some examples of the growing reach of air pollution. I'm going to talk about the links between air pollution and climate change, because I think that's really important, and there's an opportunity now to make pretty significant advances on the climate side by dealing with air pollution. There's, I think, a window of opportunity there that we're working to try to realize. I'll talk just a little bit about the regional implications and impacts for this air pollution issue. And then I'm going to talk a little bit at the end about, again, the policy implications in attempts to quantify the opportunities and then try to demonstrate the opportunities. So when we think of air pollution, I think most of us think of the urban environments as the really critical environments in the large cities of the world. And for the first time ever, we now have more people living worldwide in cities than we do in rural areas. So that's been a transformation. And especially the large cities, the reason people go to the cities is largely for increased opportunities, intense activities. The mega cities of the world are large generators of the regional GDP. But because of that intensity, they also tend to see the pollution problems first. But also, the megacities typically are also where the pollution actions, the policies are played out first. Take cities of the world, Beijing, Delhi. When they get around to doing it in that country, those regions occur first because they have the intellectual capacity, they have the money, and they have the political capacity to move things forward as people are living there and highly motivated. But we certainly are learning, and we certainly learned in the 70s and 80s that there could be a regional component to air pollution. And now we're learning, and Amsterdam was a great example. In the 70s, we saw the impact of, first to the loss of fish in the beautiful lakes of Sweden, far away from any local sources, and then we began to realize the range of air pollution. And we're now beginning to realize that that range of air pollution is beyond the regional scale. So we started with the urban environment. We've developed methods to try to deal with urban pollution. We realized there's a regional component. We're beginning to think about regional aspects of control, although those are not so easy. But now we're even faced with the growing understanding that perhaps even to manage the air quality of California, we're going to have to give much more thought to what's happening in Europe and Asia, for the rest of the Northern Hemisphere, if we're going to reach our air quality targets. So there's many ways that we know about this growing reach of air pollution, but especially on globalization, but really it's come with our abilities of satellite capabilities. If we can see pollution at a global scale, have the capacity to detect pollution at a global scale, we can begin then to make the connection that pollutants can transport long distances. Our first example of that is in wind-blown dust. The early satellites were able to see detect dust plumes being transported, at least attenuation by dust, and we could then begin to see the globalization. Now we have the capacity to see other trace species. So one that we can see from space is we're showing here CO. Actually, no, I'm sorry. The slide itself is NO2. And so we have polar orbiting satellites that are looking, following the sun and looking at the absorption of the NO2 molecule, and you can see now mapping out these large concentrations. So the darker, the redder the color, the higher the concentrations. And then you begin to see in the northern hemisphere, you pick out the hot spots of Asia, Europe, North America. Then you see the southern hemisphere has a much different picture. It's not so associated with the large populated areas, but instead are more associated with the biomass burning signals. So NO2 arises from combustion, and so we see that in the southern hemisphere. We can also begin to look for the signal of the globalization of air pollution by looking at historic measurements of ozone. So ozone is a really important molecule. Ozone is something that we're very good at making. It's a major element of photochemical smog. So at the Earth's surface where we live is a product of our anthropogenic emissions, along with some natural emissions. We make ozone. So ozone near the surface is bad, but ozone in the stratosphere is good because it filters UV radiation. It's played a big role in allowing life to exist as we know it on this planet. But in terms of the bad ozone, the photochemical smog component, we have historical measurements going back into the late 1800s. And those were done, monks were doing it in well-documented techniques wet chemical techniques that were able to reproduce and to validate that they have value. And so we put those together with the more modern record, and you can see that, and these are at isolated areas, mountain sites in remote or at least very rural areas of the globe, and you can see that the level of ozone in the global levels of ozone have increased significantly from about 10 to 15 parts per billion going back to the late 1800s to now we're at levels that concentrations are approaching above 40 to 50. So we've seen a triple of the global background of ozone. And I'm going to come back to this because our understanding of this is still not, we can't reproduce this in models. We can get present day levels pretty good, but we can't get the background levels, these long ago levels very well calculated. But this is going to have implication as I talk forward, because even these levels of 45, 50 parts per billion we're learning have impacts to plants. And so we have to be concerned with this growing background. So there's this rising background, but there's also this, again, as our population increases, we have growing numbers of pollutant levels around the world. And there's a recent study that was done called the Global Burden of Disease. And this is now being updated. I think it's under review right now. But they looked at all the different causes of disease from a health perspective and smoking, AIDS, other related activities, and looked at air pollution. And if you look at the air pollution contribution, these are the number of people at risk for high cardiovascular problems, either mortality or morbidity globally in the year 2000. And by this estimate, under current levels of pollution, you're seeing large numbers, and this is believed to be a conservative estimate of perhaps a million excess deaths per year. And in the U.S., avoidable deaths, if you will, due to elevated level of air pollution are under 50,000. And so the air pollution exposure and its impact to the global public health is very significant. And this slide just indicates the number of diseases already that have a strong quantitative link to a negative health outcome to exposure to air pollution, be it either things like ozone, primary pollutants, ozone or sulfur dioxide, but also particles are a big, in many regions of the world, the health implications of the fine particles is the major health indication. Not everywhere, but growing regions. So I mentioned this very briefly, that our understanding that the global environment, or certainly the hemispheric background levels of pollutions are increasing, and that's really very important. And let me just start, if we think of it from an air quality management perspective. So if I have an ozone concentration in Iowa, and we don't think of Iowa as having a large ozone problem, but the western part of the state is now getting really close to being in violation from the new ozone standards. And so the entire western U.S., including the mountainous region, are experiencing rising levels of ozone. But anywhere where we have the ozone or any pollutant level, we can think about that from an air quality management perspective. There's going to be a component of that air pollution that's due to local activities. Then there's going to be another component that's contributing that's coming from outside my local environment, but still from the national level. So think of the U.S. So we can think of, so Iowa has a local contribution, then we have a large regional contribution. So this is really what a nation has under its control, this portion. Then we have another component that's coming from outside our political borders, so that's the international component. And then we have another component that's natural, and from a pollution perspective, the definition of natural is not really solid. So natural could be wildfires coming from lightning. Okay, we think of natural as being also other forest fires, but of course we know that those other forest fires in general, be lit by lightning or by accidental fires, also are related to human management of that resource. So it's not necessarily an absolutely natural component. We also think of natural as biogenic emissions, say hydrocarbons being emitted naturally by plants. A certain type of plants are heavy emitters of natural hydrocarbons. So those would be then contributing to pollution levels. So those are the components that we have. We don't have much control over the natural, but there is anthropogenic emissions that can be controlled in these, but obviously from a local perspective, our ability to influence those decisions are becoming difficult. So we have this picture, but the other component that's happening, so we have air quality standards. And let's take U.S. as an example. So if we go back just as little as 10 years ago, our understanding at the time, air quality standards are the standards that are set by a nation to manage risk of exposure of their population to pollution. It's not a safe level. It's a level upon which society has decided is acceptable. There's still going to be people at risk, be them already old, people that are already sick, or young people, but for the general bulk of the population, these are perceived as safe levels at the time. So we started more than 10 years ago with a 1-hour average of 120. We then recognized with growing information on the health implications of air pollution that it's not only the acute exposure, but also a longer-term exposure. And so they went to an 8-hour standard. And the 8-hour standard moved down to 75 parts per billion. And now, right now, there's public discussion, and it's going to go somewhere between 60 and 70 parts per billion. It's yet to be determined. But so you can see that what society in the U.S. and the same is happening in China, in Europe, the air quality standards as we learn more only become more stringent. And so that means that the acceptable level is getting lower and lower. And you get to a region where the standard is such that you need to begin to bring in regional strategies. And the new standard is, for some regions of the U.S., is going to implicate that we need to be thinking about the global hemisphere. So what's happening elsewhere outside of our nation is going to be necessary to have some influence on that if we're going to achieve the level of safety that we're targeting. And again, it's because this hemispheric background is increasing. So this is putting, and this recognition that it goes even beyond a regional component is really quite important, and is beginning to challenge the nations to be much more proactive internationally, even from a pollution perspective. So just to give you an idea from the regional nature of this, how important it is from local and regional perspective, I'm showing you some work that some of us are involved with, looking at the wintertime air pollution levels of particulate pollution in the Midwest. This is a model simulation, but the observations show this very well, also show this well. So in the wintertime, in the Midwest region that you're seeing here, we often have, in these, you can see this is in January, and this is the simulation, so you can see this regional buildup of fine particles. In this particular case, there's a lot of fine particles there, but ammonium nitrate is a large component, and that's a secondary pollutant that is formed, it requires three components. It requires NOx emissions, such as those coming from fossil fuel combustion power plants, for example, automobiles. Requires ammonia, and ammonia in the Midwest is largely of agricultural component, but ammonia also can come out of catalytic converters in your vehicles and other sources. And then it requires cold temperatures, well, we have those in the winter, and we need also high humidity conditions. And so when we have conditions where snow is melting, we have those conditions frequently in the Midwest. But the point of this is, so the U.S. air quality standard right now on a 24-hour average is 35 micrograms per cubic meter. On an annual basis, it's 15. And in the wintertime in the Midwest, we can get levels that are, in some places in the Midwest, we can get values that are already at or very close to a violation just from this regional background. Iowa, the contribution in Iowa, gets us close at the current standard. We've not been in violation based on a regional background, but if you add then local emissions to that, right now Iowa's getting very close to the standard in terms of violation. And it's beginning to create some problems, especially from an economic development standpoint for the northern and eastern parts of the states. A lot of the, because if you're going to bring new industry into those regions, they have to demonstrate that that additional industry is not going to move the county into violation. And so you have to demonstrate that through model-based studies. And as it gets closer to that level, the industry, given all things being equal, would rather go to an area where they don't have to have that concern. Where they either are going to make a problem or they're going to be in an environment where the next person that comes in is going to make a problem for the region or the county. And so we're doing some research in that area. But again, it's just an example of even on a regional scale, we have, if we're going to address this, Iowa can't do this by itself. We need a regional policy for dealing with this. And we're doing some research to try to understand which of those elements do we go after, NOx, or do we go after ammonia to bring us into what's the right strategy for attacking that? And it gets into some difficult choices because going after the power plants or the automobiles, while difficult, is easier than, for example, going after agriculture. So it creates certainly thought for EPAs and regional EPAs to think about what are the options for keeping us below that air quality standard. And of course, in the particle area, the same thing is happening. So right now I mentioned the 24-hour standard is 35, and there's lots of discussion. And one doesn't know when, but one can anticipate over the next 10 years or so that air quality standard is going to get more stringent as we learn more about the negative impacts of health and the cost of that to our society. That standard is only going to go down. And if it goes down even to as little as 32 from 35, by our analysis, Iowa will be in violation, or could very well be in violation of that standard, if nothing else is done. So it's certainly an important consideration for the regional component. So trying to understand the hemispheric component. So I mentioned that was just one example of local to regional. There are many of those examples, and there's growing awareness that we got to deal with it. It's not easy. But I mentioned also that we have this growing hemispheric background, especially in the terms of ozone. And so only recently has that become a topic that has stimulated a large study that I was a part of to try to quantify, or at least to better estimate, what is the contribution from one continent to the other. So this is a study that was done by European Union under this Long-Range Transport Convention on which U.S. and Canada and Europe and many of the European nations belong. And so this was a 7-year study where we tried to look at both from modeling and observations of what we could say about this very long-range transport of fluids. So I just want to show you some results, and this has just recently been reporting been released. So what we've done here is we're using models, global scale models of atmospheric chemistry. We took each of these 4 regions, and those are both the source region and the receptor region. So what we did in the model world is just play games. So let's take East Asia. We did a calculation with all sources included. We then did a calculation where we perturbed East Asia anthropogenic emissions by 20%. We did the calculation and looked at how the pollutant distribution changed by that perturbation. So we did that for East Asia, we did it for South Asia, we did it for Europe, and we did it for North America. So these are just sensitivity studies of the anthropogenic perturbation, so we would see how the system responded to that. And what we found was some very interesting and important findings. Intuitively, going into this study, one would think, in a sense, that in the northern hemisphere, the predominant flows are west to east. So intuitively, one would think that we would have a larger, let's be U.S.-centric here, that we would be more heavily impacted by a 20% change in East Asia than we would by a 20% change in Europe emissions. And vice versa, and also that European air quality would be more sensitive to a 20% change in North America emissions than a 20% change in East Asia emissions. So again, I'm going to show you a slide for ozone, which is a fairly long-lived gas. And let's just take North America, this slide as an example. So the red indicates that when I change North American emissions by 20%, when I average that change over the entire North America grid, square that I showed you, I got a unit response. I changed it by 1 parts per billion. So the absolute value isn't that critical here, but just think of 1. Okay, so, and that makes sense. The largest perturbation should be to our own emissions. I change it by 20%, I get a response of an annual average, surface level, regional average of 1 part per billion. Then I perturb Europe by the same amount. And again, Europe is significantly downwind of North America, or okay? And so it's a long ways from getting back to, it's a long source from where North America exists, but a 20% perturbation in European emissions is 20% as important as that 20% change to the U.S., and that's a big number. And it's a long ways away, so it shows us that connection. And then East Asia, yeah, it's slightly bigger, but it's for all practical purposes the same amount. In South Asia, the perturbation of 20% to South Asia is about a factor of 2 smaller. But that's really a problem of the experiment, because of those 4 regions, the total emissions of South Asia is half of what Europe, Europe and North America. So all 3 of those were about the same emissions, so we perturbed the emissions by the same amount. The Indian emissions we perturbed by, effectively the total amount was 50% less. But if we sum all those together, it's about 0.5. So that tells us that, again, that those distant sources are about half as important as what we're doing naturally in terms of thinking about the future. So that's a surprising number. The surprising number is, A, the size of that contribution from external sources. And the second surprising thing was that it really didn't matter in terms of these long-term averages where that perturbation of emissions occurred in North America, in the Northern Hemisphere. That's what's happening, is that we're all contributing to this global background. And in some sense, that's a very good finding, because that takes away this mindset that, it should take away, and I think it's slowly taking away that mindset that what happens in North America, we only have to look at China and blame China and other parts of East Asia for what they're doing, and not paying attention to what other regions are doing. So it allows us, I think, to be a little more collaborative, at least an opportunity to be more collaborative in the future moving forward. If you look at East Asia, as an example, same thing, shows up 20% perturbation in East Asia, gives you a big response, almost the same in North America. And then you see the contributions to China or East Asia by perturbation of North American emissions, pretty big, 20%. Europe, equally as important, and South Asia, a little bit more important because it's a little closer. So actually, the external contribution to ozone in China is actually larger. The ratio of these is the influence of the external sources is actually larger for East Asia. That's 65. U.S. is about 45% as important. Europe is the largest at 75%. What's happening outside of Europe? So these are pretty interesting and important results, and it's actually stimulating a lot of discussion. So that's for ozone, and that's just the change of concentration. But those change of concentrations then could be run through impact analysis, and also would been analyzed to look at how close it is to causing us be closer to either farther in violation or closer to being in violation. The same thing was done for the particulate emissions, and so the same sorts of experiments were done by perturbing emissions in more regions. This particular case, the same from North America, South Asia, East Asia, Southeast Asia, Australia. So more over in India would divide out. So even finer structure was done here. And looking at the change of those emissions, so let's take an example here. So let's take Europe, okay? So when I perturb European emissions by some quantity, and then they calculated the change of fine particle levels, and then ran that change of fine particle levels through a health assessment that looked at mortality outcomes. And the mortality outcome metric used was adults 30 years or older. There's pretty good statistics for how changes of exposure lead to negative health outcomes. And so so this is taking European emissions, perturbing them, calculating the change of PM 2.5 levels globally, and for all regions outside Europe, calculating how many deaths that European emissions caused. Okay. And so this is thousands of deaths, and so that's why it's called export. So this is Europe's influence on the global burden of mortality outside of Europe, the rest of the world. And you can compare that to the import, and that is perturbation, to what's happening everywhere else in the region in terms of the import is everywhere else in the region. So you can see there's different. But the point is that that this transport of emissions globally of PM 2.5 is having a very, very important outcome. And to put that in perspective, by this report's estimate, the intercontinental transport of PM 2.5 into the U.S., so not U.S. origin, but into the U.S., is resulting in about 120 excess deaths per year. And just to put that into perspective, when we're changing our air quality standard, when we went from 84 to 75, the analysis showed that dramatic change in air quality standard was put into place to save between 1,300 and 3,500 premature deaths. And so you can see how if one's doing a counting of mortality, again, the national standard took great action at great expense to alleviate or avoid, on the order of 2,000 excess deaths. And the input of fine particles being transported into the U.S. is adding 1,200 deaths. So air pollutants I've talked about so far are ozone and PM 2.5, and they're primary pollutants, and I've talked about this global stretch of going from local to regional to now global, and from just an air quality perspective. But these aerosols I want to spend a few minutes talking about have other implications as well. The aerosols in the atmosphere they're small particles, and so they can influence us by being able to penetrate our lungs. But they're also the size that they interact with visible light. And so they have profound implications for the energy balance of the atmosphere. And so the aerosol is very, very important. And typically we look at aerosols here. This is a composition of aerosols that we look at for South Asia. It's actually a mixture of compounds. I'm going to spend a fair amount of time talking about black carbon, but you can see kind of the composition, a lot of sulfate coming from sulfur content, in this area largely from coal combustion. You see a contribution from ammonia nitrate, windblown dust, fly ash. But simply, most of these compounds, most of the organic compounds, and all the rest of these compounds, except for a component of dust, are scattering sunlight. And they play a role in the climate system. If they scatter sunlight, they're going to end up cooling the atmosphere, so they reflect. So we think of those as white aerosol. Black carbon, by its name, and by its function, it absorbs solar radiation. And so it is able to, as a consequence of that absorption, it warms the atmosphere. So when we think of the aerosol composition, the black carbon is acting like a greenhouse gas. And the rest of the aerosols are acting to mask the greenhouse effect, the greenhouse gas warming component. And so a lot of work is going into trying to understand that. So here's a map of black carbon distributions. All aerosols, be they white or be they black, are, by the fact that they're absorbing and scattering radiation, the net result by the time I'm a photon leaving the sun, reaching the Earth's surface, is that I'm less likely to make it to the surface. So there's a dimming. So the more aerosol I have, the less sunlight, the less number of photons reaches the Earth's surface, regardless of whether I'm black or white. But in the atmosphere above the surface, if I'm a black particle, I'm going to warm the atmosphere, and I act like a greenhouse gas. We've done some recent work, Ramanathan and I have looked at this from the Asian perspective, and by our estimate, these brown clouds, we call them, this mixture of particles that are scattering and absorbing radiation, ozone, which is a pollutant but also can absorb radiation, is that the net effect of the current pollution levels is that it's actually net cooling. And so it's masking the power of the commitment that we have to global warming due to the CO2 that's already in the atmosphere. And so an issue of thinking forward is that if we try to improve the pollution levels and take aerosol out of the atmosphere, while we need to do that from an air quality perspective, it's going to begin to take the blanket off of this masking of the global warming. And so the CO2 is there, and we're committed to that. But when we start to peel away the air pollutants, we could unravel or decrease the masking effect and see the full power of CO2. So that's a critical issue that's gotten us to think about what are the possibilities moving forward from a policy perspective. And so these particles that we're going to spend some more time talking about, black carbon and other, can be transported long distances. We've talked about that. One of the regions that's of great concern when we think about these particles that are interacting with sunlight, another way that they can change the climate system is that they can be deposited onto snow surfaces. And so we recently did a large field experiment for NASA looking at the transport of particles and air pollution. This is an April case where we transported it into the polar region, and we did a flight going to the North Pole to look at the distribution of black carbon and other aerosols and other pollutants. The issue here is that when they deposit onto ice surfaces, the black particles and the dust particles can actually absorb solar radiation. They heat up and can accelerate the melting of the ice and snow. And so that's a negative feedback to the climate system. So it's an important component, and it's an important component anywhere where we have long-standing ice. And one of those regions is the third pole in the Himalaya region. And as part of this project, we're collaborating with a group. There's an Italian group that has set up a station at the base station to the southern assault to Himalayas. It's at 5,300 meters. And Betsy in the audience has also done a lot of work in the Nepal region to look at how black carbon and other components in the region and also outside the region can be transported to high altitudes. What we find from these Italian measurements in this project is that we can find pollution levels of black carbon at this site at 5,100 meters in the springtime. And it's associated with regional scale fires, and also the onset of the monsoon tends to push material up the mountain face at high altitude. There the issue is, again, the deposition of this onto the glaciers there can accelerate the melting of that. And that region is extremely valuable because it's the water fountain of Asia. It feeds those seven major rivers upon which most of Asia's population and natural resources depend. So water resources is a big issue. Again, you see this connection between pollution levels being transported and the pollution interacting with the climate system or the regional climate system. Also, now people are beginning to look at the activities of these atmospheric ground clouds, both ozone and these fine particles, in terms of agricultural productivity. Again, if I have high levels of aerosol in the region, I have less photons reaching the plant surfaces, so the photosynthetic activity is slowed down and becomes more inefficient. And that can happen because of the particles. So that's making the dimming, less photons reaching the surface. Ozone in the atmosphere also damages crop yields in a different way. So the ozone is highly reactive. It can be brought into the plant stomata. Chemical reactions occur, and then you begin to damage the photosynthetic mechanism of the plant. And so both of those, less sunlight reaching the Earth's surface for photolysis, for photosynthesis, and then damaging the photosynthesis machinery leads to the impact of these pollutants on yield. If you trace the wet season harvest in Asia, you can see obviously this tremendous green revolution, the growth of increased yields. But recently, in this century, we see a slowing of that growth. And again, you can speculate. There's not been a definitive study, but if you also look at the increased levels of regional scale pollution, there's a suggestion that this ground cloud activity is interfering with that. And again, the ozone levels that are impacting, that we have to be concerned with from an agricultural perspective, are not these 1 hour high ozone values, and not even the 8 hour ozone levels, but it's really the exposure of the plant through the entire growth cycle. And so a new metric that's being used for looking at crop yield is the accumulated exposure to the plant during the growing hours, during the daylight hours above some threshold level. So this is a 40 ppb threshold level. But again, we think of this hemispheric background as rising and already beyond the 40 to 50. And so from an agricultural perspective, it's quite possibly that, that we're committed to damage, and all we can do is try to mitigate that damage by reducing the background levels. But it has, you can see here, the drag on yield is real, and it's a significant concern, especially if we go into a situation where it's exacerbated by changing climate that puts additional pressures on water resources for things like agriculture. Another connection between So we have the air pollution problem, and I just alluded to this connection between air pollution and climate. And so there's a whole bunch of gases in the atmosphere and pollutants in the atmosphere that impact the climate system. And so a lot of attention has been brought forward very recently to pay attention to these non-CO2 climate warmers. And here's a recent summary table. So ozone in the troposphere, that same thing I talked about is a major component of photochemical smog, is a strong greenhouse gas, especially in the upper part of the lower atmosphere, where by this a contribution of 20%. Methane is also a very strong greenhouse gas. We know that comes from things like agriculture, from coal mines, from any anaerobic bacteria activity. We know it's a greenhouse gas, but there's more awareness that not only is it a greenhouse gas, but it also plays a very important role in making ozone in the atmosphere. So methane has a kind of a double-edged sword in this game. Control of methane can reduce tropospheric ozone levels, which again, so would reduce the warming of tropospheric ozone, and it will also make less ozone. So it gets, and it's also a greenhouse gas itself. So methane is moving forward in terms of a target for climate and air quality, global pollution as a target set of strategies. The halocarbons, or the replacement chemicals for the CFCs, are also very important greenhouse gases. They're very strong greenhouse gases. This is also brought into some really good policy because we have great success in managing the stratospheric ozone hole by introducing these chemicals, highly regulated. Worldwide production is going down, replacement chemicals are coming in. So people are beginning to say, should we not use that mechanism, the Montreal Protocol mechanism, as a strategy now, add to that, at least in this area, a climate component. And then the black carbon is one that we work very heavily on, in that it's uncertain, but it could be as high as 50% as important as CO2. And so if we add up all these non-CO2 sources, collectively, they are of similar magnitude as CO2. And so this has begun to, this gives attention for opportunities for dealing with climate change by not having a complete sole focus on CO2. CO2 has to be the dominant focus. We're not going to stabilize the climate at any target temperature in the long term without dealing with CO2. But the difficulty of dealing with CO2 cannot be underestimated as well. And so what are the opportunities by dealing with these other ones? And so we're very interested and done a lot of work in trying to promote black carbon because A, it's a very strongly linked to air pollution and human health. Also, there are many things we can do to reduce black carbon. And the other side of it is, whatever I do to black carbon today, it's out of the atmosphere. It has a lifetime of a few days to a week or so. So whatever I do today, if I replaced, I went to clean diesel, that black carbon emitted yesterday is not relevant to the climate system any longer. So I have an immediate response to the system. On the other hand, CO2 emitted, that CO2 molecule emitted today, 20-30% is still here 1,000 years from now. So so the immediate action, and so there's a lot of attention. What can we do in the air pollution domain to come up with win-win strategies? So very simply, from a health perspective, all the strategies are really focused on reducing the amount of small particles, or the mass of small particles in the atmosphere. And most of the health indications don't really say one species is worse than another, although there is growing evidence that some things, like black carbon, perhaps others, perhaps have a stronger link to health outcomes. But from generally right now, the state of the health sciences that we just want to go after and reduce the aerosol mass. And so that's a win strategy from the health perspective. But from a climate perspective, because I have these white particles which are cooling the atmosphere and the black particles that are warming the atmosphere, the climate strategy for reduction is not just to reduce the mass, but to drive down the absorbing or the black carbon component faster than the other components. So can we find strategies where we can preferentially remove VCs faster than we can these other components? But before leaving that, so from a climate perspective, what really matters from this pollution levels is the ratio of this, the relative amounts of black carbon to the scattered ones. And so it also begs the question, and this brings in I know you had a lecture here maybe earlier in the semester on geoengineering. So this ratio is important. And so if I wanted to continue or to cool the atmosphere, all I have to do is change this ratio. So one way I could change this ratio is to add more scatterers into the atmosphere. So I could actually put particles in the atmosphere. Sulfur would be one. I could build more power plants That's not an effective geoengineering because they're emitted too low, but you'd want to put sulfur higher in the upper atmosphere, and that would be a fun thing. Again, so this ratio is important from climate. It's just a relative change, but from a health perspective, we need to decrease the exposure. And so this is really the question that's really come forward is, are there strategies by focusing on black carbon? Can we find ways to aggressively reduce black carbon? And the nice thing about black carbon is it comes from a lot of different sectors. That means it's coming out of diesel, it's coming out of cook stoves, it's coming out of poorly designed industrial boilers, and it has strong indoor and outdoor components to it. But the other nice thing about black carbon is that, unlike CO2, where there's this differential of the CO2 emitted per country or per person, where we have vastly different emissions per capita depending on where they are, that's not the case for black carbon. The black carbon emission per capita is pretty similar, within a factor of 2 or so of each other. And it doesn't matter whether I'm in Europe, I have a black carbon problem because I have a lot of diesels, and I have a lot of congestion, and so I'm having a health impact of black carbon, just as Beijing and India are having it. They might be due to different reasons, but everybody has a win strategy, immediate win strategy by reducing black carbon. And so one can think about moving forward, are we on a path that is going to lead us to a win-win strategy where we're going to be reducing pollution levels and reducing them in a way that's going to have this climate benefit as well. We've done some analysis, it's a little bit old now, where we looked at the best scenarios from the last intergovernmental report on climate change, where they looked at possible emission scenarios by region, depending upon, they have a whole bunch of them. A1B is a little bit business as usual, although it's based on implementing current legislation, a few things moving forward, so it's not just business as usual total, but it has some environmental capabilities in it. B1 is a much more aggressive strategy, a much greener outlook for the next couple of decades. And so these were scenarios that the report built upon. We ran them through our models in terms of looking at the change of the pollution levels and also this change of the ratio of BC to the scattering aerosol, so the black versus the white aerosol. And the first maps here are so essentially looking out to 2020. This is the change of aerosols, and the bright colors are all positive numbers, so pollution levels got worse. Under the A1B scenario, increased exposure, increased damage to human health, increased damage to agriculture. If we follow that path, that's the path we're on. Even under the very much more aggressive scenario, again, all these colors are positive, not as large, all positive. So from the health standpoint, these scenarios don't give us a win strategy by themselves. The good news is on the climate side, these scenarios actually had that's because pollution levels are increasing, and so the scattering aerosols are increasing faster than the black carbon. So we're not on that path. And unfortunately, over the last 5 years or so, one can see global emissions are really following much more on the A1B scenario than we are on the B1 scenario. They're continuing to increase in important ways. So we're not on that path, but the question is, can we get on that path? Are there ways now that we know a little bit more about the system and these opportunities for win-win scenarios? So are there real ways that we can realize reductions of pollution levels and at the same time changing that ratio in a positive way? And it's a real challenge because I'm going to talk about some things here, but there's no source where only black carbon comes out. I don't have a black carbon only source. If I have a forest fire, if I have a cook stove, I'm getting black carbon, which is absorbing, but I'm getting a whole bunch of other stuff that's scattering. So for each source sector, for each fuel that's used, and for a lot of different activities, there's a whole bunch of things that are emitted at the same time. And so we really have to look very carefully at the sectors and the blend of those sectors to see whether or not there are any real ways that we can perturb the system in a way that has a climate link. So we just completed a UNEP WMO integrated assessment report looking at the opportunities for reducing tropospheric ozone and black carbon to deal with this climate issue. And the report for policymakers has just been released. The report itself is still being printed. It's not, the full report is not out yet. But the good news is, by looking very specifically at source sectors, by taking into account the co-pollutants, by putting them through models and doing some cost estimates, there seem to be, identified in these are actual measures that offer winning opportunities. And the measures that are focused on BC are looking at things like high emitting sources. So this is a heavy duty truck that's fairly, and this is not even loaded, it's super emitter. Substitution for clean fuels for cooking, banning agricultural waste burning, improved enforcement of regulations. So a lot of these, more specifically, looking at cook stoves, these high emitters, largely those are in the developing areas. In Europe, it's looking at even higher efficiency diesel particle traps, and also at the higher latitudes, looking at fire heating. Scandinavian countries do a lot of wood burning and replacing the traditional stoves and fireplaces with better designed fireplaces, because that turns out to be a large emission source. And at the higher latitudes, they have a larger impact on the Arctic region, which is one of the most susceptible regions. So by our analysis, by the team's analysis here, this is what the report offers, is opportunities. This is a busy slide, but let me just look here at the CO2 at the reference scenario. Okay, the reference scenario is looking at the A1B scenario for the future if CO2 is going to grow along those lines. What's plotted here is the continual growth of CO2 as the reference and the temperature change of the global atmosphere. And this is the relationship between these and the temperature response is still highly uncertain, but this is our best estimate. You can see the uncertainty range here is the height of the green bar. So we're on a path right now for perhaps leading to a 3-degree change of temperature. And up until very recently, and I think what the next IPCC report will talk about, I don't think they've actually determined, but the previous IPCC report talked about 2 degrees as our magic target. If we can stay below 2 degrees, there's a higher likelihood that we're going to avoid any serious and quick climate change disruptions. So 2 has been the target that people have been trying to find measures. Can we stabilize below 2-degree change of global temperature? There's some new research that's coming out that is arguing that 2 degrees is too much. That it needs to be worse than it needs to be kept less than that, but that's still an open discussion. So here's the reference scenario. If we just look at CO2 measures alone in this report, and we looked at it from a cost and technology, the ones that can actually be done over this time scale, you can see that CO2 measures alone still don't do it. They don't get us there in time. If we go out longer, if we go to the end of the century and early the next century, again, CO2 is going to have to do it for us. But when we looked at the methane and the black carbon measures, and largely black carbon is an important one early on, you can see that we take a much different path over the next couple of decades, that we're able to move with a much slower rise of temperature. And we get to the point where CO2 growth is again taking over any reduction that we're getting from the pollution side of it. But you can see we're on a much different path. But if we only did those, we buy time for several decades, which is critical, because hopefully we get smarter and technology gets better, that we can do these CO2 measures faster than we can project now. And then if you see that if we actually do those together, the methane, the BC, and the CO2 measures from this package of options together, you can see that there's an opportunity to stay below 2 degrees. And the really nice thing about these is that there's a lot of synergism between, many times BC measures and some of it is switching fuels, and some of those fuels will have a lower CO2 emission, and so there's win-win strategies within the measure. It's dealing both with the reduction of CO2 and with the reduction of black carbon because of the efficiency of being able to provide the energy or whatever the need of that is. And so this report then goes on to say, okay, this is the temperature side of the story. Then running those, the changes of pollution levels through the crop model and the human health models, you can see if we go to these measures of treating CO2 and the short-lived climate forcers as a combined strategy, you can see that we have even just the pollution levels has the largest impact on the avoided crop yield losses. Those are 50 million tons estimated. And from a human life perspective, also the short-lived the air pollution has the largest impact on the human health, avoiding 2 million excess premature deaths from that. So this UNEP report is optimistic within our understanding and with a large degree of uncertainty that there really are measures that are low-hanging. There's no technology limitation to implementing these right now. There's no need for breakthrough technologies. There are things that we can do. It's a question of putting in place the policy, the infrastructure, the financing that would allow those to happen. So let me just end then. So this report has taken and identified some opportunities. The question now, there's a lot of discussion, and there's international interest in moving forward. At national levels, the US EPA is very interested. The international levels, the cooperation is really pretty exciting for doing this. And so we're working with Scripps Ramanathan on, he's designed an experiment where he wants to go out and document that we can implement some of these mitigation strategies at large scale, so at the village scale implementation, and the idea of trying to create a hole in this atmospheric ground cloud, so by this and actually documenting it. And here, the technologies being looked at are really, it's a tough one because the cook stoves are critical. A long history of improved cook stoves that haven't worked for a variety of reasons, haven't made a large penetration, and so, but if one can get in there, then that's the strategy that's been identified along with some biogas production. And just recently completed a very small pilot project looking at a few homes in the village. And this is indoor measurements of black carbon in this particular village house. And you can see for 3 hours a day, the black carbon concentrations are more than 100 micrograms, can reach more than 100 micrograms per cubic meter at all of the cooking times. These are huge exposures to black carbon. In polluted areas, you can see black carbon, 0.5 to 1 microgram per cubic meter is an indication. You're in a polluted environment. These are very, very much higher than that. And because there's so many cook stoves, the outside environment is also highly polluted. So the idea is to go in with these interventions at the village scale of 10,000 to measure this village before the interventions. They have a large-scale interventions of penetration of cook stoves and other components, and then do our best to measure and document, and both using in-situ measurements, but also to look at the regional scale detection capabilities. So let me close with this. Again, hopefully you have a better understanding that there is this expanding global component of even air pollution, and that the management moving forward of air pollution really is going to require a larger view of what's happening in the northern hemisphere. And so this idea, that has implications. The idea is that you know, that we can only worry about China or also things that we were doing before with this globalization. You think of all the outsourcing of manufacturing where we were moving our dirty industries to China because A, it's lower cost, and B, environmental costs to us are less stringent. But I like to say that's a little bit like being a Girl Scout and building your latrine, you know, upstream of your campsite because you know, you can't go far enough in the northern hemisphere. It doesn't matter where it's coming out; it's adding to the background levels, and we have to manage this collectively at the background level. So that's one important component. But with that growing recognition has also come this recognition of the closer coupling between the air pollutants and their role in the climate system. And so now I have multiple ways I can approach the climate and the air pollutant system. If my air pollution is my number one problem and I'm going to have to do things in the future, I may be able to do things smarter and I may get some benefits, or somebody may pay me to do something a little smarter if I also have a climate benefit. If I'm driven by climate policy, then the air quality opportunities then bring a whole other set of tools that I can use in the next couple of decades to really tackle the climate problem. So I think it really is an exciting time, and it's gotten a lot of attention, and people want to do things in this window of opportunity of dealing with the short-lived climate forcing is really a pretty hot topic right now. So I'll stop there. Thank you.